Hello everyone and welcome back. In this lecture, we're going to wrap up our lesson on projections and coordinate systems by talking about common coordinate systems that you should know how to use. To begin with, we'll cover UTM, which is one of the most important global coordinate systems in use today. And then we'll talk about the Albers projection, which is commonly used across large regions of the Earth for accuracy of different areas. And then finally, we'll wrap up with the state plane and public land survey system, a very confusing set of coordinate systems that you at least need to be introduced to if you work in the United States. We won't spend too much time on it though, since so many of you aren't. To start out, let's discuss UTM. We can figure out what it's doing just by its name. UTM stands for Universal Transverse Mercator Projection. So think about from the previous lecture what transverse and mercator meant. Transverse meaning rotated 90 degrees, and mercator meaning a certain type of cylindrical projection. Great. The universal in the name is because this is a series of 60 projections where each one has a different standard parallel. Each item in the series is called a zone and covers 6 degrees of longitude from the equator up to one pole or the other, and the standard parallel optimizes for that area. You can show data outside of the zone, but it'll be more distorted than the data that is inside of the zone. UTM also uses what we call a false northing and a false easting, which is a way to say that the origin point of each zone isn't 0, 0. The 0, 0 point is located well outside of the zone so that all the coordinate values within each zone are positive. The northing and easting values defined in the projection parameters tell the GIS system to do this. Now, while there are many smaller latitudinal zones in UTM, we generally divide it up in half, north and south. So when specifying coordinates, you specify the zone and whether it's in the northern or the southern hemisphere. Here in Northern California, we're in zone 10 north or 10N, and coordinates will be relative to that UTM zone. I think the reason so many people, myself included, like UTM and make use of it is not just that it provides good accuracy in each zone, but that it provides a common framework that covers the whole globe that is easy to understand. So that if I know how to use UTM in my area, I can go to a whole new place on the globe and still use UTM just in a different zone. This makes it very practical for use across different applications and disciplines because you can communicate with people even if your coordinate systems are different. Next up, we have the Albers projection. Albers is a conic projection, and it's often modified and used to build more specific projections. It's also an equal area projection, which means it preserves areas, but not necessarily many of the other properties. The Albers projection is also a form of secant projection. Remember that cone that we sunk into the Earth? And this means it has 2 standard parallels, or the lines along the Earth along which there's no distortion. And these account for its ability to accurately represent large areas. The Albers projection isn't just one projection, but more the basis for many other projections that cover areas large and small. It can cover areas as large as the United States, and there's a projection for that, or Russia, and there's a projection for that, or even just California. Next up, let's talk about the state plane coordinate system and the public land survey system, which are specific to the United States. They're mostly beyond the scope of this course, but if you do much surveying or work with county data in the US, do yourself a favor and go read up on it. Those of you in other countries don't really need to know this, except as an example of an unfortunately difficult way of specifying locations. The first thing to note is that it's not really a projection. It's a coordinate system that's built on the transverse Mercator and Lambert conformal conic projections. It's often used for surveying because it's highly accurate within each zone, but it's a very bad way to store data outside of each zone. And because it uses simple Cartesian coordinates, which enables easy calculations. Remember, this stuff all happened in the days before computers, so that's a huge bonus to make calculations simpler. If your data or projects cross boundaries though, you're better off using UTM. The way it achieves some of this accuracy is by dividing up the United States into 124 zones that mostly follow county lines. And within each of those, there's a separate projection that makes it more accurate in that area. Now, the state plane coordinate system itself is fine and relatively simple, but built on top of it is the public land survey system, which involves a nested set of coordinate systems and gets pretty complicated very quickly. In the public land survey system, state plane zones get divided up into quadrangles, townships, and sections. Each quadrangle is a 4x4 grid of townships, and each township is 6x6 miles, or 36 square miles, and contains sections of 1 by 1 mile each, or 36 sections. Each section is then divided into quarters, and those quarters into quarters again. Inside each section, Cartesian coordinates specify locations. Now, you can imagine how confusing this is. You're probably confused right now. To get a location, you might go to the southwest quarter of the northeast quarter of the section in Township 2 South and 3 West. That's how you'd specify a location. While it's still used in lands management in the United States, it's not widely used elsewhere, and I recommend different coordinate systems when possible because of this difficulty in specifying locations and the conceptual difficulty just to understand how to work with it. In some disciplines, though, you do need to use it. That's all I'll say about the public land survey system. If you think you need to know more about it, there's plenty to read online, including calculators and converters for location. Those of you in the US at least need to know it exists so that when you encounter it, you'll know that it works a little differently and that it is a valid coordinate system that you can use to translate to whatever you work with. There will be a link to a Wikipedia summary of the system on the resources for this video. Okay, to wrap up these common coordinate systems, we covered UTM. It's a relatively simple global set of coordinate systems that provide great accuracy in each zone and compatibility worldwide. We also discussed Albers projections, which are commonly used throughout the world as well, but without the standardization that UTM has. And then we discussed the state plane and public land survey system, which are often confusing but are widely used in surveying land in the United States. Okay, that's it for this lecture on common coordinate systems. In the next lecture, we'll put some of this into practice to really round out your knowledge of coordinate systems and how they're used in GIS. See you there.